Today we're going to talk about other dimensions, but we're going to get there rather gradually by looking first at the differences between 2 and 3 dimensions, and then between 3 and more dimensions than 3, and how that eventually relates to physics, and why cosmologists and physicists take very seriously the idea that there may be more dimensions to our universe than the 3 we walk around in. Well, the most obvious difference between 2 dimensions and 3 dimensions is indicated by this illustration on a flat surface, that on a flat surface, if you draw a closed curve, it separates the whole of the surface into 2 different disjoint pieces. So if you're here in the Gresham Lecture Theatre, if not part of the in-crowd, at least crowded in, then if there is a boundary here, you cannot pass into the out-crowd region without cutting through the boundary. And this means that in 2 dimensions, you can only do very simple things with networks of wirings or nerve systems, anything that involves paths or chains. If they're going to cross, they have to intersect. And intersection can mean short circuit or a problem. Now, of course, if you go to 3 dimensions, this is no longer the case, because you can have complicated, convoluted paths that pass over and under one another. You can have paths passing across one another without intersecting. So this little picture here, sort of the M25, sort of somewhere around Heathrow, you can see that in 3 dimensions you have the first opportunity to have considerable complexity. If you look in the volumes of mathematics and mathematical physics and you look at the sort of theorems that mathematicians seek to prove, they often try to prove a result in any number of dimensions. And in geometry and topology, you very often find the result is proven in all dimensions except 3. Sometimes 3 and 4. 3 and 4 dimensions are especially complicated and difficult. Once you go beyond 3 and 4, there's no new complexity arising. Here is another picture. That's not really the road layout around the M25 that's planned in the future. This is, actually. But so this, for example, is a picture of the trajectories projected onto 2 dimensions, are 3-dimensional trajectories of a chaotic dynamical system. And you can see how the 3-dimensionality is fully exploited by the complexity of things that can go on. The trajectories never intersect, but they overlap and pass over and under one another very often. Well, living in 2 dimensions then is likely to be a simple affair, if not impossible. And if you feel that your life is falling apart recently, then it may be because you're living in only 2 dimensions. So you see, if you have this 2-dimensional creature here, then its sort of digestive system requires it to fall into 2 pieces. So again, the message is, in 2 dimensions, you are forced to be rather simple in many respects. Now, in the 19th century, there was great fascination with the question of other dimensions, both fewer dimensions than 3 and more dimensions than 3. One that you'll know about, Fantasy About a 2-Dimensional World, by Edwin Abbott, who I think was headmaster of City of London School, was a little fantasy about what it might be like to live in a world of only 2 dimensions on a flat surface. There are all sorts of little social messages about this, and perhaps even religious ones as well. Other people wrote analogous stories later on called Sphereland, about life on the surface of a ball, which, although 2-dimensional, is curved. In Abbott's little story, you remember that the characters who appear, their status in society, in the flat society, depends on how many sides they have. Women, unfortunately, just have the one side in the story. As you move up, you become a little more important. You're a triangle as a soldier, a worker, a merchant, a mercer perhaps, professional, gentleman, of course, nobleman, and finally, with an infinite number of sides, in a sense, if you're a circle, a high priest. Now, the point of this little picture is just to show you how there is a limiting process here, that as you go through polygons, so flat figures with sides of equal length, as you add more and more sides, you approximate more and more completely to a circle. However, the important thing to notice is that there is no limit to the number of regular polygons that there can be on a flat surface. So you can have any number of sides that you choose to these polygons, all the way up to any finite number you like. In the limit, you'll get a circle. So previously I gave you an example of how 2 dimensions was simpler than 3 dimensions. But in the respect of having these regular figures, 3 dimensions seems much simpler than 2. Because although there are an infinite number of 2-dimensional polygons, there are only 5 regular polyhedra in 3 dimensions. And this was known to the ancient Greeks thousands of years ago: the tetrahedron, the cube, the octahedron, dodecahedron, the icosahedron. So 12 and 30 sides here. So these are the only regular 3-dimensional figures that exist. Staying with the Victorians, their fascination with extra dimensions of space was closely bound up with growing beliefs in the spirit world and spiritism, and whether these extra dimensions could be the reason for psychic phenomena and so forth. You remember even people like Arthur Conan Doyle believed, it seems, in fairies at the end of his garden, and took rather seriously ghosts and spirits and so forth. Well, there was a society that was set up in Cambridge that still exists, the Psychic Society, with many famous physicists involved, like Crookes, to investigate some of these phenomena. And one of the focal points of the investigation was the trial of the infamous Henry Slade, who I think it's probably fair to say was a confidence trickster, who really preyed on unsuspecting people, I think largely young ladies, claiming to have contact with another spirit world. Well, he was eventually tried for fraud, and part of his defense was that the tricks and the unusual things that he was doing were possible because he had access to a 4th dimension. So he could take an object out of a sealed bottle, move it outside without unsealing the bottle, because he was able to move it into another dimension. Well, he was found guilty and jailed eventually in 1877, but the process of evaluating his claims was put in the hands of Zollner and Peter Tate. Tate was a famous Scottish mathematician, collaborator of Lord Kelvin, famous for the mathematical theory of knots, which he invented, and also of golf. And they set a number of little tests for Mr. Slade to demonstrate whether he really did have access to another dimension. So he was provided with 2 rings, 2 closed rings, and he had to join them in some way. And then he was given a spiral. It was a snail, a right-handed one. He had to turn it into a left-handed snail. And he was given a knot on a loop of string, and he had to unknot the knot, and then he had to turn a right-handed granny knot into a left-handed one on the loop of string, and then he had to do the little problem of getting an object out of the sealed bottle. Well, you can see why these are relevant considerations. So if you're living, let's go down a dimension to flatland, and imagine the flatland trial of Henry Slade. So we've got 2 flat spiral snails here, and the challenge is to turn the one of one-handedness into the other. And to do that, if you move into the 3rd dimension, you lift the spiral up into the 3rd dimension and put it down, you can do it. And similarly with the bottle, we can lift the object upwards out of the plane into the 3rd dimension, put it back down over there. And you can change right-handed and left-handed people around, again by lifting flat person up, twisting them over, putting them down again. So these were the simple tasks that he was being asked to do, and unfortunately he failed. Well, the last of the great Victorian eccentrics was involved in this, who eventually did something rather profound, was Charles Hinton. Now, Hinton had a perhaps unfortunate family background. His father, James, seemed to start a new type of religion in Victorian England, which was unlikely to be popular in that climate. So it preached free love and polygamy. So it's not very Victorian. And Charles Hinton grew up in this family background. He went to Oxford, and then he taught for a while at Cheltenham Ladies' College, and then at Uppingham School. And he married the widow of Boole, the founder of set theory. So he married Mary Boole. Unfortunately, when he married her, he was already married to Maud Weldon. So he had taken this idea of polygamy perhaps too seriously. And this caused a big scandal. He was on trial for bigamy and jailed for a little while, and then he went to the USA. Well, despite his interest in polygamy, he's also interested in polygons and in higher dimensions. And when he went off to America, he went to Princeton, invented the baseball machine, you know, the automatic pitching machine. Then he seemed to have lost his job for some reason in Princeton, and he ended up in the patent office in 1908, 1905 period in America, at the same time that Einstein was working in a patent office in Europe. Now, what he did when he was there was really quite insightful. There was still great interest in higher dimensions. And he realized that if you thought carefully about what was the relationship with 2- and 3-dimensional objects, you could gain insight into what 4-dimensional objects would look like. So he did this in several ways, and he produced some pictures which now are still rather fascinating, both to artists and to mathematicians. So he pointed out that suppose we look at a 3-dimensional cube and we project it onto a 2-dimensional surface, or we just look at it in the distance. And you know what it looks like. It looks rather like a sort of framed picture. You see one face here, another face here, and these 4 lines joining the 2 squares. And you think about it, if you were to look at a square in projection, you look at the cube in projection, and so on, you work up a dimension. What would it look like if you shone the torch on a 4-dimensional hypercube? Well, the structure is analogous. You get a cube surrounded by a cube joined by all these 4-sided faces. So this is what the shadow of the 4-dimensional cube will look like. So he goes on and asks other ways in which you have a relation between dimensions. If we move a point, a 0-dimensional thing, if we move it, we create a line. It has 1 dimension higher. If we move the line, we draw out a square, 2 dimensions. If we move the square sideways, it drags out a cube. So if we were to drag the cube, we will get a 4-dimensional object, which in projection looks like this, just as this is the cube seen in projection on the 2-dimensional surface. The last and most famous of these little games that he played was unwrapping a cube. So if you imagine that you've made a little cubic box out of paper and you unwrap it, you know what it looks like. It's got 6 squares making it up. The flat sheet of paper out of which it was made looks like that. So if you wrap it up on the 2 sides, wrap this over, you will eventually be able to make a cube. So what would happen if you unwrapped a 4-dimensional cube? Well, the analogy works in just the same way. Instead of having the 6 1-dimension lower squares, you have this collection of cubes. So this is what the unwrapped hypercube looks like. Well, if you like various aspects of modern art, you will have seen this picture before. Mid-1950s, Salvador Dali's famous corpus hypercubus, representation of the crucifixion. This is the hypercube that's been put here. Dali had a lot of interaction with mathematicians at this period, and then some years later, learning about what was happening in higher dimensional geometry and how to use some of these higher dimensional images artistically. Also around the early years of the century, there were other artistic movements. Picasso, of course, the picture of Dora Maar, there are many versions of this picture. An attempt to break out of the two-dimensional aspect of the flat image by giving views from two perspectives, as it were, as though you were sitting in a fourth dimension and looking at two possible projections. Well, all these revolutionary things in geometry were developing fast in the early years of the 20th century. Einstein showed how you thought about four-dimensional geometries of space-time, and it became a revolutionary area of mathematics. And if it's revolutionary, then there's one man who would probably be interested in it, and even Lenin, Vladimir Lenin became interested in some matters of cosmology and geometry and wrote a little paper about them. And when asked about n-dimensional geometries, he made this sort of remarkable statement that mathematics may explore the fourth dimension, but the Tsar can be overthrown only in the third dimension. You know, it's rather like Titanic lost, no parrots hurt headline in the Parrots Weekly. Well, so this is the background of mathematics. So mathematicians are used to dealing with spaces with any number of dimension. They're quite familiar with them. They recognize that the dimension introduces a critical element in the structure of the spaces and what's possible within them. Now, what's happened in the last 10 to 12 years within physics is that physicists have begun to take very seriously the possibility that space may have many more dimensions than the three that we're familiar with. Now, the first person that saw clearly that there was a connection between the dimension of space and the sort of physics that goes on within it, or astronomy, was actually the philosopher Immanuel Kant. Now, we know him most famously towards the end of the 18th century as a great critical philosopher, but in his early years, before his interest changed, he was quite a serious scientist and dedicated Newtonian. He had a theory of the origin of the solar system and wrote about many other areas of mathematics and astronomy. One of his most interesting observations was in writing a little article about why space had three dimensions. He realized that there was a deep connection between the three dimensions of space and the inverse square law of gravity, which he admired so greatly, which Newton had discovered. And he pointed out that if one looks closely at the form of force laws in physics, whether it's gravity, electromagnetism, anything else, the form of the law is related to the number of dimensions of space. So an inverse square law arises, it's the number of dimensions minus 1. If we lived in a universe with 4 dimensions of space, we would see inverse cube laws everywhere. So he argued that because he thought Newton's law was sacrosanct, this was the reason why we had 3 dimensions. The logic's the wrong way round. We would now say it's because we live in a 3-dimensional world that we see inverse square laws dictating the force of gravity and of electricity and magnetism in nature. So what this shows you is that there is an intimate connection between the nature of physics, the forms of the forces of nature, and the constants of proportionality, the constants of nature that sit in front of them, and the number of dimensions of space. And we'll see what has really emerged as you look at this more closely is that you soon learn, in Orwellian sense, that 3 dimensions are good and all other dimensions are bad. Well, why is that? Well, if you start to look closely at some of the simple but important aspects of the makeup of the world. Suppose you look at the structure of atoms. Then, as we all know and appreciate, matter is stable, at least on extraordinarily long time scales, billions and billions and billions of years. But if you change the number of dimensions of space, but the mathematical forms of the laws remain the same, you discover that stable atoms cannot exist in any other dimension bigger than 3. So there can't be any atoms, any molecules, any you or me, hyperversions of you or me, in more than 3 dimensions. So there's something very special about 3-dimensional worlds. So you can't have any complexity. What's happening here is that the force laws, because as you raise the number of dimensions, the forces fall off as a higher power than a square, the forces get too weak to hold anything together. And this same argument, it turns out, applies if you start to look at the form of gravity when you have more dimensions. That you can't hold anything together by gravity either. There are no planets, there are no stars, everything is very dull and boring. So it's a universe that would be unknowable by minds, which are built in a complex way out of atoms or any other structures that hold together. So there is something quite unique about having a world with 3 large dimensions. And in 1955, Gerald Whitrow, London University, wrote a famous paper called Why is the World Three-Dimensional?, in which he argued simply we would have to find the world to be 3-dimensional because we couldn't exist in a world which didn't have 3 dimensions of space. Well, you can be more radical still. You can embed this information I've just given you in a picture where you allow the number of dimensions of time to be different as well as the number of dimensions of space. So we are here in a world with 3 dimensions of space and 1 of time. If we attempt to have 1 time dimension and more dimensions of space, so I've just said it's unstable, there are no atoms, there are no planets. The same would happen if you try to have lots of dimensions of time. If you try to be down here in worlds with just 1 or 2 total dimensions, everything is too simple. Again, turns out you can't have any gravitational forces and you can't have any complexity. If you try to stray off into these other parts of the picture, something very odd happens. The whole structure of cause and effect in physics is changed, and the future is no longer determined by the present. One of the reasons for this is if you ask what happens to waves or signals when you send them in any number of dimensions, then there is something again very special about 3-dimensional worlds. So in worlds that have an even number of space dimensions, the wave signals don't just go at one speed, they go at a wave speed and any speed less than that wave speed. And that means that if you send off 2 signals at the same time, they will arrive at their destination at different times. Or worse still, signals that are emitted at different times arrive at the same time. And that's what we call reverberation. So if you stick with odd-numbered dimensional spaces, you don't have that problem. But only in 3 dimensions are the signals undistorted as they propagate. So the whole sending and receiving of signals has a very special and simple property in 3-dimensional worlds that's completely lost in any other number of dimensions. So I stress that these arguments are being applied to universes and worlds where the dimensions are all thought to be the same. They're all big. So it's a whole democratic business. They all have the same status. Now, in recent years, as particle physicists have attempted to develop a so-called theory of everything, to join together all the forces of nature, they've discovered that such a quest is only possible in worlds which have many more dimensions than 3. If you try to do it in a smaller number of in 3 dimensions, then you turn out to get infinite answers for the prediction of all sorts of observable quantities. There's something horribly wrong with the theory. And only if you have 9 dimensions of space or 10 dimensions of space can you fit in all the different forces of nature, the join them together in the jigsaw, and the theory is completely finite and well behaved. So for this reason, particle physicists take very seriously the idea that there are more dimensions than 3, that having a single unified theory of the world is only possible, it appears, in worlds with 9 or 10 dimensions of space, 10 or 11 dimensions of space and time. So how do we reconcile that with this picture? I've just been telling you that if you have 10 dimensions, there are no atoms, there's no us, we couldn't be here. Well, as you probably noticed, we don't live in a 10-dimensional world. We don't walk around in such a world. But the way in which we try to reconcile that with the expectation that there are many more dimensions is to propose that the dimensions are really not democratic. They're not all the same size. They don't behave in the same way. But here's a picture of the expanding universe that we talked about in past lectures. The size of the universe, the extent of the expansion against its age. Expanding universe, all the dimensions would increase with time. And one proposal is that what happens here is that 3 dimensions expand, 3 dimensions eventually become very large, and we walk around in them. The remaining dimensions do not. They remain fantastically small, perhaps as small as this special Planck unit of distance that we introduced in the past talks, where quantum theory and gravity become one. So the idea is that 3 dimensions have become big, and the other dimensions are fantastically small, perhaps imperceptibly small. Nobody knows what is the force or the physical process that would be responsible for trapping these dimensions, nor do they know why 3 dimensions become big. You know, is this some feature of the theory that it has to be 3, or is it random? Could it be in some parts of the universe that it's a different number, or does it have to be the same everywhere? But as we've just seen, if it was a random process and it was different from one part of the universe to another, we could only expect to find ourselves living in one of the regions where 3 dimensions had become big. Well, one of the consequences of believing that the world really has many more dimensions of space is that things like the laws of nature, the constants of nature that we're in the habit of observing, measuring in the laboratory, the true constants of nature live in the total number of dimensions. And the things that we measure in our laboratories are like the shadows, the 3-dimensional shadows of those 10-dimensional constants. And a remarkable consequence of these theories is that if there are other dimensions which are not changing, so they're static and they're very small, if they were to start to change or wobble or oscillate in some way, we would see that. And we would see it because our 3-dimensional constants of nature, things like the charge on an electron, the strength of gravity and so on, would be observed to change at the same rate. So curiously, changes in the other dimensions have direct observational consequences for what we see in our 3 dimensions. Now this idea has developed another strand in recent years. And what the strand is goes by the name of brane worlds. The word brane world you'll sometimes see, or p-branes, n-branes. It's just a version of membrane, okay? A brane being a surface that has any number of dimensions. So the picture that physicists have developed is to think of perhaps the 10-dimensional world as being some large so-called bulk volume, and we live as a 3-dimensional surface on that large volume. So this complete volume of everything is called the bulk, and the 3-dimensional surface on which we live is called the brane. And as we've seen, what we're expecting then is that in the early stages of the universe, this surface expanded, become very large, and the other dimensions did not. Now, one of the variants of things on this brain is the following. That in these theories it appears that the natural structure is for the local forces of nature, things like electromagnetism, radioactivity, strong nuclear forces. So the things that are the most strong forces of nature, they act just in our three-dimensional brain world that we live in. So their effects only propagate within the three dimensions. And as a result, atoms exist in those three dimensions, and waves propagate in nice ways, and so on. But the force of gravity is unusual. It propagates both in our three-dimensional brain world, but it also propagates out into these bulk world of other dimensions. And why would you want to have such a picture? Well, it gives you a natural explanation as to why gravity is so much weaker than the other forces of nature. So gravity is about 10 to the 40 times weaker than electromagnetism. And this type of picture rather naturally leads to that type of demarcation. You can see the force lines of gravity not only extend in the three dimensions, but they propagate out into all the other dimensions as well. And so the fraction of the force lines acting in the three dimensions is comparatively lower, and gravity appears to be much weaker. Now, one of the challenges that you now face is first of all deciding how big are these extra dimensions if they really exist. I gave you an example that said that they might be as small as the Planck length, but we shouldn't assume that that's necessarily true. And in these theories there are two types of scenario that you can pursue. So the first is to indeed take seriously the idea that the number of dimensions are very, very small, that they're close to that Planck length. And if that's the case, then you have some problems because their structure, their nature is all tied up with the complexities of the theory of quantum gravity that dictates what goes on those scales. And if you remember that as the universe begins to expand from that size, after just a little while it may undergo this dramatic process of inflation. And if that were to happen, it would rather erase memory of some of the things that happened earlier on in the universe when it was this size. Now, in the last few years, it's been noticed that it is possible in these theories to have a somewhat different type of brain world picture, which would allow the extra dimensions to be really quite large. So if you're in the scenario where gravity reaches into the other dimensions and the other forces don't, it's possible for the other dimensions to be a fraction of a millimeter, a tenth, a hundredth. They could be much smaller, of course, so you could regard this as the biggest size, and it could be anywhere down to this. So this is really quite big, a tenth, hundredth of a millimeter. You're looking at the size of a tiny insect's leg or something like that. So this is almost macroscopic. This is something that you could virtually see. But what you would be wanting to see, what you could see, would be simply the effects of gravity as it reached out into those other dimensions. Now, this sounds an easy thing to look at, because if there's just one more extra dimension, suppose we live in a four-dimensional world, three are big, and one extra dimension is a tiny fraction of a millimeter, then down on the scales of length smaller than a fraction of a millimeter, Newton's inverse square law of gravity would be dramatically changed. It would become an inverse 1 over r to the fourth law. So there would be a very big change in the form of gravity. So at first you think, oh, this would be easy to check. But remarkably, you can't do it. That there is no way of testing Newton's law of gravity down on scales less than a tenth or a hundredth of a millimeter. It's very poorly tested law of nature on small scales. And the reason is because gravity is so weak. So you've just got to watch a fly walking on the ceiling to realize that the adhesive force, chemical force between the fly and the ceiling is much, much stronger than the force of gravity. If you hold quite a heavy mass with a magnet here, magnetism is much, much stronger than gravity. So in all the situations you might try to set up in laboratory, these other forces, surface forces, friction, magnetism, they interfere with the situation that you can't isolate gravity. So you can't get your hands on it to test Newton's law of gravitation in isolation. And if you're a physics student or you have any old physics textbooks at home, look up at the back of the book the values of the constants of nature, and you'll see Newton's constant of gravitation very, very poorly known. Many, many decimal places less than that of any other constants of nature. So this is a reflection of how weak gravity is, how difficult it is to test Newton's law of gravitation. It may be in the future that one can do better in space, in an environment with very, very low temperature, almost no friction. Well, another feature that's a problem here is that you can't turn gravity off. You can measure electrostatic and magnetic forces because you can measure changes in those forces very easily. We're very good at measuring changes in things. Because electric charge and magnetic poles come in opposite flavors, you can have a positive electric charge and a negative one. You add them together, they cancel. You take one away, you've suddenly got a positive or a negative charge. Similarly with magnets. But you can't turn gravity off. The analogue of charge or a magnetic pole for gravity is mass. And mass only comes in positive varieties. So you can't turn gravity off and measure the change, and therefore measure its strength. So you're rather trapped. Everything gravitates, and you can't turn it off. So one of the great challenges in physics at the moment for experimentalists is to think of a test of Newton's law of gravity, to which Einstein's law reduces, on these very, very small length scales. So think of a space experiment or a lab experiment where you can really test whether gravity behaves in the same way as it does, say, over these dimensions. And the payoff is very great. This is a direct test as to whether there are extra dimensions of space into which the gravitational force field is reaching. If these extra dimensions are fantastically small and you're living in this situation, then you won't see those effects experimentally. You will have to look at cosmological consequences of other dimensions. Well, these brane worlds, finally, can have all sorts of other curious features. So if we think of our three-dimensional brane world, as it were, it's like a little slice, it's like this piece of paper, and we've been thinking so far as if it were a surface with a large bulk volume attached to it, and we walk around on this surface here. But this surface can be folded in sort of exotic ways. So we could be folded in an S shape like this. So what this would in effect mean is that we might be living on one fold of the surface, but there would be another fold very, very close to us. So that would be just the same as if there was another dimension which could be just a fraction of a millimeter away from us. So other dimensions can be very, very close. And the reason they can be very close is that we can't see or feel them except through these gravitational effects on scales which are very, very tiny, where the magnitude of the strength of the effects are correspondingly incredibly small. What I've drawn here is a sort of provocative little example that astronomers are sort of amused by. Suppose you have a world that has this S shape here, and we're sitting over here, and we are looking through our telescopes at a galaxy far away in the universe, and we may take a photographic image of it. And let's suppose that the situation is indeed that forces like electricity and magnetism just live and move on the brain surface. Three-dimensional surface, but it's now folded. Gravity, on the other hand, can go everywhere, can reach into all the dimensions, so it both goes along the surface, but it goes off out of the surface, so it can go off into the other dimensions. Now, what happens when light is emitted by this galaxy to our telescope? Well, the light path has to remain on the brain sheet, and so it takes this long, tortuous path to our telescopes through space, all the way along the brain surface. But gravity doesn't have to do that. Gravity can reach us directly, moving in a straight line path through the extra dimensions. And so we feel the gravitational effect of the other galaxy more directly, more significantly, and more quickly than we see the image of the galaxy. So this is rather amusing. It takes billions of years for the optical signal to reach us, a far shorter time for the gravitational signal to reach us, and this might naturally lead to a situation, therefore, where you infer the existence of lots of dark matter, so that you see the gravitational effect of more objects, more galaxies in the universe than you can see the optical or radiation images of. So I hope this little snapshot has shown you that there are really some rather exotic aspects of extra dimensions. Physicists take extra dimensions seriously because for 30 or more years they have been searching for a way to join together all the different forces of nature into a single so-called theory of everything. They tried to do that in many different ways. In 1967, it was first predicted that you could do it for electricity, magnetism, and radioactivity. And then in the late 1980s, the observational evidence for that was forthcoming from CERN, and we have a so-called electroweak theory. So electricity, magnetism, radioactivity are just different manifestations of one underlying force. Subsequently, people worked rather hard to join the strong force, it's the root of nuclear processes, into this unification scheme. And so-called grand unified theories provide many candidates as to how that was possible. Now, until the early 1990s, the end of the 1980s, it was not really seen how you could ever add gravity to that story. How could you add gravity, the fourth piece of the jigsaw puzzle? Any attempt to do it, you got nonsensical answers, infinite answers. There was clearly some horrible disease in the theory. Well, then Green and Schwarz showed that if you changed one fundamental assumption in these theories, that elementary particles are just points. And the most elementary things in nature are a collection of points. Instead, you have the idea that they're little lines, they're little loops or tubes of energy that became known as strings. Then everything works rather beautifully. You can join gravity together with all the other forces. And if you knew how to calculate what happens when you made these strings oscillate, they oscillate with different energies, and each of the energies of natural oscillation, just like a guitar string, corresponds to a mass, phi equals mc squared. If you could work out those masses, you would know what we call the elementary particles of nature. But this game of explaining everything in terms of the motion and vibration of strings only works if there are many more dimensions of space than 3. So either with 10 dimensions of space or with 9 dimensions. Until 7 or 8 years ago, the situation had been reached where there were a number of these different so-called string theories. Each seemed to be self-consistent and a perfectly good working theory of everything. Now, this is rather odd. So why would you have 5 different possible theories of everything? I mean, which was the one that was used in our universe? So people were rather puzzled by this. Was it that our world had just sort of picked one? What were these other theories of everything? But then it was pointed out by Witten that there was a remarkable mathematical transformation which had been unnoticed, which turned each of these theories into any of the others when you applied it. and that they weren't actually different theories at all. They were just different views of some other theory. So they were different shadows of some bigger, deeper theory cast in different directions. In fact, they were limiting cases of the deeper theory, a low energy limit or a limit where electromagnetism was weak and so on. And the full theory, of which these 5 candidates were the shadows, is not known. It has the name of M theory. Sometimes it's called M for mystery or matrix or millennium or something like that. So the great search in fundamental physics is to try and characterize this theory more completely. And what we know about it are these shadows of it in different limiting cases. And this is a great challenge both in mathematics as well as mathematical physics to extract some of the consequences from this M theory. But the M theory has a large number of dimensions of space-time. The theory exists only if we have this large number of 10 dimensions. What's remarkable about this prediction, I always think, is that it also doesn't specify how many of those dimensions have to be space dimensions and how many have to be times. The theory all works so long as the total number of space-time dimensions equals the magic number, but it doesn't tell you whether there are 2 times or 3 times or 4 times. And that's why I showed that picture, which allowed the number of times to vary as well as the number of dimensions of space. We always assume that there is only 1 time, because if you try to allow more than 1 dimension of time, horrible things happen. Things can decay very, very rapidly. Elementary particles decay very rapidly. And you run into problems trying to conserve energy. Things do not work as we would like them to work in our world. So one of the great challenges for experimental physics at the moment is to find new probes of these ideas that there exist these extra dimensions. Some people believe they are indeed going to be fantastically small. Others live in hope that they could be really rather large. And if they are this large, you would be able to see the consequences in the next round of very high energy particle physics experiments at CERN. So every time you get a particle whose quantum wavelength is smaller than this, you would perhaps be able to see the consequences of energy leaking out into that other dimension and energy leaking in from the other dimension. So you would look for events where there was a decay of a particle into 2 particles, one of which you don't see because it goes off into the other dimensions, and one which you do. But you would know that the invisible event would have to be there in order to conserve momentum. Similarly, you might see a particle appearing from nothing and decaying into 2 particles because it came in from the other dimension. So you can search systematically for these types of events in accelerator experiments, and this will be done when the Large Hadron Collider comes online in a few years' time. So there is an experimental angle to this. There is a cosmological angle. Do we really live in a universe that emerged out of a large number of dimensions? And of course there's a geometrical and a philosophical angle, that it's really rather striking and mysterious that we may just be a little surface in a much greater, higher dimensional universe. And all the ultimate questions about the nature of the universe and its laws are almost inaccessible to us, because they're questions about the total number of dimensions. And we, rather like the ants walking around on the flat surface, don't have full access to the other dimensions where the answers to all the deep questions lie. Thank you.